Hello everyone. Today in this video we are going to talk about the similarity between a solenoid and a bar magnet, and we'll discuss Gauss law in magnetism. So after this video you should be able to explain the similarity between bar magnet and a solenoid and state Gauss law in magnetism. So this is a magnetic field due to a straight conductor. So we have concentric circle at each point of the conductor, and the direction is given by right hand thumb rule. And this is a magnetic field due to a circular loop, and if you use the right hand thumb rule in each part of a circular loop, you'll see that magnetic field lines will enter the loop from one side and comes out of the loop from another side, making one side as a north pole and another side as a south pole. So a current carrying loop act as a magnetic dipole. So this is a three-dimensional picture of a circular coil. So you can see magnetic field in each point. Here I am considering the magnetic field at 2 points only, and in next picture I'll consider the magnetic field at each point of the conductor. So you can see this is a south pole, magnetic field is going inside, and this is north pole, magnetic field is coming out of this. So when you add many turns, so magnetic field due to each turn will get added up, as you can see out here. So we'll get a strong magnetic field when you add many turns together. So a solenoid can be considered as a collection of many circular coils. So magnetic field due to each turn gets added up and we'll get a strong magnetic field, and all the magnetic field lines will enter from one side and comes out from another side, making one side north pole and another side south pole. So you can check the magnetic field lines with the bar magnet, so they are similar. So in order to know the north pole of the solenoid, you have to use the right hand thumb rule. So if you curl the finger in the direction of current, then thumb will show the direction of north pole. So these are the similarity between a solenoid and a bar magnet. So we can say a bar magnet to be a magnetic dipole because we have two poles in a bar magnet. When we suspend a current carrying solenoid, then it will point north pole and south pole of the earth as done by the bar magnet. And two current carrying solenoid also attract or repel each other as done by the bar magnet. And if you cut a bar magnet into many pieces, you will get the many magnets of small magnetic field. Similarly, if you cut a solenoid into many pieces, you will get the small solenoids with weak magnetic field. Now we will prove that a current carrying solenoid is similar to the bar magnet. So this is a solenoid in which current is flowing. So we can consider this solenoid to be collection of many turns. So from here to here is 1 turn and 2 turns, 3 turns. So we know a circular coil produces magnetic field similar to that of a small bar magnet, north pole and south pole. So if we consider this turn, there will be north pole and south pole. Similarly, for these turns also we have north pole, south pole. So it is like a collection of north pole, south pole, north pole, south pole, like this. Out here you can see north and south are together, so they attract each other, so they will neutralize each other, meaning magnetic field lines coming out of north will enter through the south, so it will not terminate out here. So all the magnetic field of all the magnets get added up and we'll get a strong magnetic field. So this will act as a one magnet. So a current carrying solenoid act as a bar magnet. So same thing I have explained it out here, you can copy it. Now we'll prove how a bar magnet is similar to a solenoid. So out here I'm considering a cylindrical bar magnet, and now I'm considering only this part of the magnet. We know there are atoms inside the bar magnet, and inside the atoms electrons are revolving, and we know when the charge revolve it produces current. So we can consider these atoms to be a current carrying loop. So suppose the electron is moving in this direction, so current will flow in this direction. So we can consider one atom to be one circular loop. So similarly, we'll have many loops in which electrons are flowing in same direction or current is flowing in same direction. So if you see this now, so all the electrons are revolving in one direction and current is in opposite direction. Now if you consider these two loops, in this loop current is flowing in downward direction and out here it is flowing in upward direction, so they will cancel each other. Similarly these two will cancel each other, so only we are left with the current in the surface only, so it will produce a surface current. If you add all the currents of all the atoms, then we'll get a surface current, so like this. So all other will get cancelled, only we are left with the current on the surface because of the flow of electrons. So if you consider all the parts of the magnet, so we'll get the current on the surface on each part of the magnet. So let's take the bar magnet again. So due to the flow of electron, we'll have surface current on the surface. Now it is looking similar to a solenoid in which current are flowing on the surface. So let me show you. So this is a solenoid and current is flowing. So this diagram is similar to the diagram of the bar magnet in which surface current was flowing. So these two are similar. So now same thing I've written out here. So because of all the electrons, we will have a surface current. So due to that surface current, this bar magnet will have magnetic property. Now we'll discuss the Gauss law in magnetism. Before that, let's understand the Gauss law in electrostatic. So in electrostatic, it says that total flux through a closed surface is equal to 1 by epsilon naught times the charge enclosed by the surface. So we know flux is equal to Q by epsilon naught. Now let me explain this with the diagram. This is an electric dipole. So suppose you consider a closed surface which is enclosing the charge out here. So out here you can see charge is plus Q and flux is Q by epsilon naught. So there is a flux through this surface. But when you consider a closed system out here, you can see the number of lines entering is equal to number of line coming out, or you can see there is no charge inside the surface. So charge is 0, flux is 0, so there is no net flux out here. So if you consider another surface which encloses both the charges, that time also you can see all the field lines coming out is equal to all the field lines going in. So total charge is plus Q minus Q, that is 0, so there is no flux. So now similarly we'll consider a magnetic dipole. So we consider a charge Qm out here, Qm plus Qm and minus Qm. So now let us consider a surface out here. So out here the magnetic charge is not there, we have 0 magnetic charge, so flux is 0. So see, 2 lines are entering and 2 lines are coming out, so that means we don't have magnetic flux. So now if you consider whole magnet, that means both the charges, so magnetic charges, so for n I am considering Qm and for this I am considering minus Qm, that is 0, and flux is equal to Qm by K. So I'm just writing another constant because we are dealing with magnetism this time, so I'll not use epsilon naught, so this K is different constant. So out here also there is no flux, that means number of lines coming out from this side is equal to the number of lines entering from this side, so there is no flux. Now if you consider only north pole, if you see the number of lines which are coming out is this many, but we know in a bar magnet, magnetic field lines go from north to south from outside the magnet, and from inside it goes from south to north. That means whatever number has come out of this surface will enter the surface from inside the magnet. That means number of lines which is coming out of the surface is equal to the number of lines entering the surface. So there is no flux. So we are just doing opposite out here. So magnetic charge is qm I'm considering, so flux is 0. So when flux is 0, qm by k is equal to 0. So qm is equal to 0. That means qm is equal to 0, meaning there is no magnetic monopole. So I cannot have a single pole of a magnet. So a magnet has to have two poles. Now let us understand this from the source of magnetic field. So inside the magnet, atoms are making the magnetic field. So in atoms, electrons are revolving in a circular path and they are acting as a circular coil. So but in a circular coil we have both north and south. We cannot have only north or only south in a circular coil. So all the atoms are having north and south. So if you collect them, you will get one north and one south. So it is not possible to get only north or only south. So according to Gauss law, the net magnetic flux through a closed surface is 0. So whether you enclose north pole or both north pole or south pole, or you don't enclose anything, every time you will get 0. But in electrostatic, net flux was equal to q by epsilon naught, but here it is always 0. Another statement, so Gauss law states that the surface integral of magnetic field over a closed surface is 0. So integration of b dot ds, that is closed integral, is always 0. So the importance of Gauss law, so Gauss law is that there is no monopoles, only north pole or only south pole. So they always exist in pairs. First and second consequences of Gauss law are same. So first one is saying there is no monopole, and second one is saying the pole always exist in pair, south pole and north pole. And the third number, if a number of magnetic field lines of a force enter a closed surface, then equal number of lines force must leave the surface. So there should not be any net flux through any surface. The flux is always 0. So now let us summarize the video. So first thing we understood that is a bar magnet and solenoid are equivalent. So we can prove a solenoid to be a bar magnet. Second is the net flux through a closed surface is 0. So this is Gauss law. And so third summary is there is no free magnetic charge. So meaning we cannot have a single north pole. So north pole and south pole always comes in pair. But in electrostatic we can have a isolated charge like only plus q and only minus q, and we can have dipole also. But in magnetism we have dipole only. So the main reason is the magnetic field is being produced by the atom, and atom is a circular loop which produces both north pole and south pole. I think this is the end of the video. So please don't forget to like the video. Thank you.